Good day. We are going to talk about thermodynamics. I am Hermelinda v. Abellanosa. Thermodynamics is a branch of physics that deals with the relationship between heat and other forms of energy. In particular, it describes how thermal energy is converted to and from other forms of energy and how it affects matter. So, thermodynamics involves the measuring of this energy. So when we speak about thermo, we are talking about heat. Dynamics is change. So on the picture, as you can see there, a burning wood, this picture, the energy we see in the form of fires not created out of nothing, but rather comes from the energy that is stored in the wood. Likewise, the wood is not destroyed, but rather is converted into ash and soot. Thermodynamics is the study of the effects of work, heat, and energy on the system. When we speak of the system, we are talking about is simply a collection of component parts that make up a whole. The universe is the largest system that we know of, and it includes all matter and all energy. So, in thermodynamics, the collection of objects on which attention is being focused is called the system, while everything else in the environment is called surroundings. So all thermodynamics can be expressed in terms of four quantities: temperature, internal energy, entropy, and heat. So according to the British scientist Snow, the three laws of thermodynamics can be summarized as in three ways also. First law of thermodynamics is you can't win. Second is you can't even break even. And third is you can get out of the game. So the concept of work, heat, and internal energy of the system are related by the first law of thermodynamics, with which an expression of law of conservation of energy. The body of this person contains internal energy. Part of this energy is used for the workout and part is lost in the form of heat carried off by evaporating sweat. So the first law of thermodynamics is an expression, an expression of the conservation of energy. This was summarized by scientists known as you can't win. The change in internal energy of the system is equal to the heat added to the system minus the work done by the system. So the formula is change in internal energy is equals to heat minus work, or done on the system, change in internal energy is equals to heat plus work. This is the reason why Snow summarizes it as you can win, because it's either a minus or a plus. So internal energy and heat. The internal energy of a system increases from an initial value to the final value. So the formula change in internal energy is equals to the internal energy final minus internal energy initial is equals to heat. In writing this equation, we use the convention that heat is positive when system gains heat and negative when the system loses heat. So talking about internal energy and work, if the system does work on its surroundings and there is no heat flow, work is positive when it is done by the system and gains heat, and negative when it is done on the system. The internal energy on a system can also change because of work. So, first law of thermodynamics is just the conservation of energy principle applied to heat, work, and the change in internal energy. A system can gain or lose energy in the form of heat and work. The internal energy of a system changes from an initial value to the final value due to heat and work. Q is positive, or heat is positive when the system gains heat, and negative when loses it. So, losing heat, negative, gaining heat, positive. W, or work, is positive when work is done by the system. Negative when work is done on the system. On the system, negative. By the system, positive. Formula, change in internal energy is equals to internal energy final minus internal energy initial, which is eventually equals to heat minus work. Illustration, A versus B. So the system gains energy in the form of heat. Illustration letter A, the system gains energy in the form of heat, but loses energy because work is done by the system. So that's why the arrow is towards the work, because the work is done by the system and heat is gained by the system. Illustration letter B, the system gains energy in the form of heat and also gains energy because work is done on the system also. So arrows are towards the system, while the other illustration, one arrow is towards the work because work done is done by the system and not on the system. Example 1, positive and negative work. System gains heat. Heat is positive. When work done by the system, work is positive. In part A, the system gains 1,500 joule of heat from its surroundings, and 2,200 joule of work is done by the system on the surroundings. In part B, the system gains 1,500 joule of heat but 2,000 joule of work is done on the system by the surroundings. In each case, determine the change in internal energy of the system. So we are going to determine the change in the internal energy of the system. So letter A, illustration. So we are going to illustrate So part A, work is done by the system and heat is gained by the system. While part B, work is done on the system and heat is gained on the system. So 1,500 joule and 2,000. The system loses more energy in doing work that it gains in the form of heat. So the internal energy of the system decrease. So change in internal energy is equals to internal energy final minus initial to be negative. Solution. Q plus 1,500. Q is equals to positive 1,500 joule gained by the system, and work is 2,200 joule done by the system. Formula is heat minus work. So 1,500 minus positive 2,200 joule, we have negative 700 joule. So the minus sign for change in internal energy indicates that the internal energy has decreased. illustration. So another solution, letter B. Q plus positive, W negative, done on the system. So negative. We have the same formula. Substitute. Heat is 1500 joule and negative work is 2200 joule. We have positive 3700 joule. The plus sign for change in internal energy indicates that the internal energy has increased. Another problem. 60 joule of work is done on a gas, and the gas loses. Remember, loses 150 joule of heat to its surroundings. What is the change in internal energy? So work done is positive and heat loss is negative. So as you illustrate it, the arrow for heat is towards the surroundings because the gas loses heat and work is in the system. That is 60 joule. So change in the internal energy is equals to 150 negative 150 joule minus 60 joule. We have negative 90 joule. Next, a gas starts with 200 joule of internal energy while you add 180 joule of heat to the gas. The gas does 70 joule of work. What is the final internal energy of the gas? So we have the change in internal energy is 100 equals to 180 joule, the one that you add, plus the negative 70 joule. We have 110 joule. So the same formula, final minus initial, internal energy final minus initial. So what do we need to know here is the final internal energy of the gas. That final internal energy of the gas is 310 joule. Another, while 40 joule of work are done on the gas, the internal energy goes down by 150 joule. What was the value of the heat? This time, the unknown is heat to the gas. So 150 joule is equals to the heat plus the work done. So we have heat is equals to negative 190 joule. A system does 164 joule of work in its environment and gains 77 joule of heat in the process. Find the change in internal energy of A, the system, and the environment. So by the system, we have the illustration. The work is done by the system. Okay, so we have 77 joule for heat and 164 joule for work. But in terms of work, system versus the environment, the work is done in the environment. Work is done by the system. And solution A, So heat is positive 77 joule gained or absorbed by the system, and 164 joule for work done by the system. Same formula. We have 77 minus 164, we have negative 87 joule. So work done by the system is greater than the heat gained. Solution B. Heat is equals to negative 77 joule lost by the environment, while work is equals to negative 164 joule done on the environment. Change in internal energy is equals to heat plus work. So, 77 negative. So, we have positive 87. Work done in the environment is greater than its heat loss. So, to summarize the first law of thermodynamics, any thermodynamic system in an equilibrium state possesses a state variable called the internal energy. Between any two equilibrium states, the change in internal energy is equal to the difference of the heat transferred into the system and the work done by the system. Okay, analogy. How applicable is the first law of thermodynamics in our day-to-day transactions regarding the bank? Balance in your bank account is a property deposits and withdrawals. So a given balance can be obtained by a series of deposits and withdrawals or a single large credits and debits. Another analogy in comparison with energy, heat minus work. So first situation, in terms of balance is deposit minus withdrawals. If there are no deposits and if you have enough balance, you can withdraw, but the balance will diminish. In terms of energy, if the system has enough energy, you can extract work without adding heat, but the energy diminish. Another, if you don't withdraw, but keep depositing, your balance will go up. In terms of energy, if you keep adding heat, but don't extract any work, the system energy will go up also. Okay, second law of thermodynamics. It is the heat flow statement. So heat flows spontaneously from a substance at a higher temperature to a substance at a lower temperature and does not flow spontaneously in the reverse direction. So as the illustration goes, heat flows from hotter to colder region. So in summary, there exists a useful thermodynamic variable called entropy. The natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. So this, in the second law of thermodynamics, we are talking about the entropy. So one example is the heat engine. A device which transforms heat into work is called a heat engine. This happens in a cyclic process. Heat engines requires a hot reservoir to supply energy and a cold reservoir to take the excess energy. QH is defined as positive and QC is negative. Another essential feature, heat is supplied to the engine at a relative high input temperature from a place called the hot reservoir. Part of the input heat is used to perform work by the working substance of the engine, which is the material within the engine that actually does the work. Example, the gasoline. Air mixture in automobile engine. The remainder of the input heat is rejected to a place called the cold reservoir, which has a temperature lower than the input temperature. So the illustration, the schematic illustration, the input heat that originates from hot reservoir, the work that the engine does, and the heat that the engine rejects to the cold reservoir. Efficiency of the heat engine. So E is equals to work done input heat, which is equals to work divided by the QH, or the heat absorbed. The efficiency of the heat engine combined equation. So E is equals to 1 minus the heat excess and the heat absorbed. A Carnot engine is a reversible engine in which all input heat originates from a hot reservoir at a single, and all rejected heat goes into the cold reservoir at a single temperature. The work done by the engine is W. It states that no irreversible engine operating between two reservoirs at a constant temperatures can have a greater efficiency than a reversible engine operating between the same temperatures. Furthermore, all reversible engines operating between the same temperature have the same efficiency. Reversible process. A process is one of which both the system and its environment can be returned to exactly the state they were in before the process occurred. So example, a Carnot engine takes in 3,000 calories of input heat and rejects 2,000 calories as waste heat. The temperature of the waste heat is 600 Celsius degree. Determine the A, efficiency of the engine, and the useful work done by the engine. So we are going to solve for what is unknown. So part A, step 1, complete the data table based on information both given and implied in the problem. So solution, absorbed heat or the taken heat is 3,000 calories and the temperature is 600 Celsius degree. So part A, step 2, determine the efficiency. So efficiency is equals to the heat absorbed or taken minus the heat excess divided by the heat absorbed, the heat waste. So substitute 3,000 calories minus 2,000 calories divided by 3,000 calories, we have 0.333 or 33.3%. Part B, step 1, solve for the useful work done by the engine. So E is equals to W divided by QH. So divided by, so E is equals to 0.333, which is equals to work, divided by the heat absorbed, 3,000 calories. So work is equals to 1,000 calories. Alternate solution, W is equals to QH minus the QL. So 3,000 calories minus 2,000 calories is equals to, W is equals to 1,000 calories. Part C, step 1, solve for the temperature of the input heat. The efficiency and the temperature of the waste heat are known, therefore, E is equals to TH minus TL divided by TH. Substitute 0.333 is equals to TH minus 873 Kelvin divided by the TH. Therefore, we have the TH is the unknown or the temperature of the input heat is equals to 1,310 Kelvin. Okay, so this law of thermodynamics, the second law of thermodynamics, is applicable and existing in the refrigeration process on the left. Work is used to remove heat from the cold reservoir and deposit heat into the hot reservoir. Compare this the engine process on the right. On the right is the engine process. On the right illustration is the engine process, while on the left illustration is the refrigeration process. But they both have in common because they summarize the second law of thermodynamics. So refrigerations, air conditioners, and heat pumps. Refrigerators and air conditioners operate by removing heat from a low temperature or the cold reservoir and exhausting the heat to a high temperature or hot reservoir. So there will be a coefficient of performance. The coefficient of performance for a refrigerator is the ratio of the heat removed from the cold region to the work performed to remove the heat. So coefficient of performance is QC divided by W. Concerning the second law of thermodynamics, it introduces the notion of entropy, a measure of system disorder. Internal energy is the quantity of a system's energy. S is the quality of the system's energy. Another, Mr. Snow's expression, not knowing, for those who do not know, or not knowing the second law of thermodynamics, is the culture equivalent to never having read Shakespeare. Implication of the second law of thermodynamics. Time marches on. Because thermodynamics talks about a reversible process, the process which you cannot reverse or you cannot return to its, you cannot restart. If you watch a movie, how do you know that you are seeing events in the order they occurred? No? For example, in watching a movie, or for example, if I drop a raw egg on the floor, it becomes extremely disordered, so greater entropy. Playing the movie in reverse would show pieces coming together to form a whole egg, decreasing entropy, highly unlikely. The greater disorder, the greater entropy. The lesser the disorder, the lesser the entropy. So direction of process. The second law helps determine the preferred direction of a process. A reversible process is one which can change state and then return to the original state. This is an idealized condition. All real processes are irreversible. Your life journey is irreversible. That is an example of the second law of thermodynamics. So life is, you make the most of your life because you cannot reverse what had happened. Practical uses. Automobile engines, refrigerators, and air conditioners are all work on a principle laid out by the second law of thermodynamics. Have you ever wondered why you can't cool your kitchen in a hot summer by leaving the refrigerator's door open? Feel the air coming off the back. You heat the air outside to cool the air inside. If you are going to analyze it, you will see you can't really break even. As what Mr. Snow summarized the second law of thermodynamics. Third law of thermodynamics is summarized by Snow, scientist Snow, as you can't get out of the game. No system can reach absolute zero. There is one reason we use This is one reason we use Kelvin temperature scale. Not only is the internal energy proportional to temperature, but you never have to worry about dividing by zero in an equation. There is no formula associated with third law of thermodynamics. Implications. What is the implication, or what are the implications of third law of thermodynamics? According to MIT, researchers achieved 450 picokelvin in 2003, less than one-half of 1 billionth. Molecules near these temperatures have been called the fifth state of matter, the Bose-Einstein condensates. Awesome things like superfluidity and superconductivity happens at these temperatures. So the zeroth law of thermodynamics. The first and the second law were well entrenched, with an additional law was recognized. If objects A and B are each in thermal equilibrium with object C, then A and B are in thermal equilibrium with each other. Allows us to define temperature relative to an established standard. So to summarize, thermodynamic equilibrium: when two objects are separately in thermodynamic equilibrium with a third object, they are in equilibrium with each other. So objects in thermodynamic equilibrium have the same temperature. That's all. Thank you.